Okay, here's problem 4 from the 8.9 part 2 worksheet. All right, now we saw this recursive definition in section 8.8 worksheet. Just to jog your memory a little bit, we start out with the initial case gives us a dot. Recursive rule applied once gives us that thing. Applied a second time gives us that thing. Applied a third time gives us that. Applied a fourth time. So recursive rule 1 once, recursive rule twice, recursive rule 3 times, recursive rule 4 times. And well, okay, you see the pattern. Right, notice that each of these are complete graphs. Right, and that's what we're going to prove. That's the property. The property is that everything in S is a complete graph. All right, so base case. All right, let's say P of X first. X is a complete graph. Okay. All right, so we're proving this for the initial case of our recursively defined set S. The initial case starts with a single vertex. All right, so remember what a complete graph is. A complete graph is the graph that contains all possible edges. All right, a single vertex can have no edges. Right, this is because, remember, an edge is defined, let's say U and V, if you have an edge there, right? This is really defined as the two-element subset of the vertex set. Can have no edges. Because there are no two-element subsets of the vertex set. Right, here we just have one singular vertex. The vertex set is V, right? So there's no two-element subsets of that, right? Because if you think about it, right, V, remember in set theory, this is the same set as that. So there really is no two-element subsets of the vertex set. And so therefore there's no edges. So, and a complete graph has all possible edges. Well, there are no possible edges for a single vertex, so it has all of them. Okay. So a single vertex is a, let me put in parentheses, boring complete graph. Okay. So a single vertex is a complete graph, but it's a really boring one. But in any case, it's still a complete graph. All right. So that's the base case. All right, let me do the inductive step. I'm going to need some more room for that. Okay, so here we're going to say, suppose x is in S and P of x is true. It's a little windy in my garage. Okay. And then also we're going to say, okay, so this is our inductive assumption, is that x, that P of x is true, right? That x is a complete graph. And now we're going to suppose that y was created from x using the recursive rule. All right, so let's think about how that works. All right, so here, let's say we have x is a complete graph, or just that x is actually a complete graph, right? We're assuming that. Okay, and then now y is the graph formed by creating a new vertex and connecting that to all of the old vertices of x. So the whole thing is y. Y. Okay. All right, so remember, a complete graph has all possible edges. So our assumption is that x has all possible edges. And then we just need to show that y has all possible edges. So because of the way the recursive rule is defined, y, the new vertex gets connected to everything else. So everything was connected to everything in the old graph, and now everything will be connected in the new graph. Right, so that's the idea. Okay, so we're going to prove P of y. All right, I'll write that as want to show P of y. Okay. All right, so really we want to show that y is a complete graph. We want to show that y, which was created from x, right? I'll just draw that again. Got some new vertex. This guy's connected to all the old vertices to make y. So we're going to explain why the graph y has all possible edges. Okay, so I want to show or explain why this graph y has all possible edges. Okay, so let's see. Let's think about this, right? Now, a lot of different ways you could go about this. You could be intuitive and just say, okay, look, x has all possible edges, right? So when you add a new vertex, the only possible new edges are edges between old vertices and y, and the new vertex, let's give the new vertex a name. Let's say V. Okay. I think that'll basically do it. Okay, let's just say, let's call the new vertex V. Okay. Let's say since X is a complete graph, it has all possible edges. It has, since X is a complete graph, it has all possible edges between between any vertex of Y, let's say between any vertex of Y that is not V. All right, so what I'm saying is, what I'm doing is I'm using the inductive hypothesis here. I'm saying, okay, since X is a complete graph, we know that inside X, without thinking about these new edges that we've added to create Y, we know all of those possible edges are there. Okay, that's using the inductive assumption P of X, that X is a complete graph in and of itself. Okay. Okay, so by the recursive rule, all of the new edges between old vertices of X and V will be in Y. So Y has all possible edges. So Y is complete, or is a complete graph. Right. Now, lucky me, I have an eraser. So I can go like that. I can go like that. I can go like that. And now I have a nice looking proof. Too bad for you. If that happened, you'd have to get a new piece of paper or something to turn in a nice looking proof.